All right. Oh man, did you watch that Packers game last night?
Disturbing.
Man, that was it was bothersome. But for those of you who are tennis fans, though, at least you got to watch the Federer match opposite that. Did you watch it?
Yeah.
Man, that didn't look like it was going to go very well. I was down 2 match points in the fourth set, and somehow came back and then just destroyed him in the fifth. The guy just decided to stop playing. It's a pretty interesting match. Much more entertaining than the Packers game.
I watched your lecture during the Packers game.
What's that?
I watched your lecture during the Packers game.
Oh. So you watched me instead of the Packers game, so I'm more entertaining than that Packers game.
Well, yeah.
I'm okay with that. Okay, so let's, did we finish talking about the Mac stuff last time?
They said that you said we were going to pick up. I thought that we kind of finished. We were talking about proprietary stuff.
Okay, so let's just kind of finish up Apple OSs for a few minutes here. So eventually we got past this idea of needing that blue box where now, a bunch of software is out for OS X and we don't have to worry about it anymore, blah, blah, blah. So Apple kept coming out with new operating systems named after cats. And their most recent one is actually named after the waves in the San Francisco Bay, called Mavericks. In any case, most people would say that the Mac OS X is a solid operating system. Most of that is due to its being based on Unix, right? Now, there have been some interesting features added to the Mac operating system over the last several years, which have been then adopted by some other companies. Windows actually hasn't adopted as many of them as they probably should have, but it's made its way into some other software products. One of these things is a technology called Opencl. Anybody familiar with Opencl? Or heard of Opencl? Ever heard of Opencl?
Might have.
Huh?
I don't know what it is, but I think I heard it.
You might have? Okay.
It's like DirectX.
Hmm?
Like DirectX. Just DirectX.
Well, Opencl utilizes, it deals with CPU management. So the idea is this. Your computer processor is a general purpose processor. It knows how to do 1,000 different magic tricks, right? But every single computer has a graphics card in it, a GPU, so a graphic processing unit. And that guy is not general purpose. It's just very, very, very good at math. And a lot of aspects of our computers, in terms of performance, is all math stuff. So Opencl is a software framework which monitors the stuff that your computer is being asked to do, and it offloads part of that, things that could be done more efficiently by the graphics card, to the graphics card. Make sense? So in that particular case, for some applications, having a good graphics card benefits your computer in terms of processing power. So now your graphics card isn't just used for video games. Because at the end of the day, if you have a $800 graphics card or a $60 graphics card, it doesn't really matter if you're running Word. Microsoft Word's going to look every bit as high definition as it did on the more expensive graphics card. Now, if you're running a high-end video game with a bunch of crap happening on the screen at once, well, then the better graphics card is going to shine. But since most of the time, our computers, well, hopefully most of the time, for some of you probably not most of the time, but since most of the time our computers are running things non-video games, it would be nice for us to take advantage of the processing power of our graphics card rather than just taking up electricity, right? So that's what Opencl is, and it was introduced in Mac, I want to say it was possibly Lion or Mountain Lion, somewhere in there, where they introduced Opencl. But some cool technologies like that, which sometimes you have an operating system that comes out that looks the same as the previous one, but actually under the hood there's some new technology. And Mountain Lion was one of those. So I'm thinking maybe it was Mountain Lion. All right, so the Apple OS keeps evolving To a lesser degree, the Windows operating systems keep evolving. Most of what we see now is interface changes. We hear Microsoft talk very little about new technology. Does it seem to you that Microsoft just kind of rests on its laurels with regard to its operating systems? It has a huge market lead. We don't really see them bragging about their operating systems, right? That's not really kind of where they make their money anymore in terms of selling. People automatically upgrade to the newest thing just because a zillion computers come with it, so Microsoft's getting their licensing agreement. So they kind of control that market without even having to try. Microsoft tends to put their money into some other things. All right. So let's talk about how our computer actually works. When you first turn your computer on, at least on a PC, you usually see kind of a black screen that has, like you might say starting OS or something like that. Okay, this is a little piece of software called the Bootstrap Program. So it's the program that comes before the operating system. This guy knows how to load an operating system. Sometimes there's even another program that sits in between called the bootloader. Common bootloaders on Linux would be Lilo, and that's Linux Loader, and Grub. Mac has its own. If you've ever seen when a Mac boots up, you can hold down the Option key and it gives you which, you can choose which hard drive to boot off of. Same thing with Windows. What is it? F8? You can press F8 over and over again and it gives you some options on how do you want to boot. So in any case, the Bootstrap program is a small little piece of software that actually lives on the motherboard. Okay? Typically stored in ROM, read-only memory. It's known as firmware. Firmware is kind of an interesting software-hardware hybrid. It's usually a piece of software that lives directly inside of a piece of hardware. And to upgrade it, you have to flash that entire hardware. Put a whole new program on there. So Bootstrap is what takes your computer from power on to actually running operating system. It's the guy in the middle that does all the handoffs. All right. So initializes all aspects of the system, loads operating system kernel, and starts execution, blah, blah, blah. So here's our computer system organization. All of our computers have one or more CPUs. Sometimes these are physical CPUs. Sometimes they're a single CPU with multiple cores in it, which acts as multiple physical CPUs. We have device controllers that connect through something that's a common bus. So we'll kind of talk about that, the picture here below. So down here, we have this bus. So think of it as a single highway. And on this single highway, we have all of our different aspects of our computer operating. So our processor, when it receives information and sends information, it's doing that over that highway. We have our disk controllers, which control our hard drives and CD-ROMs and DVDs and floppy disks if you have an older computer. You have our USB controller, which is another piece of hardware that controls stuff that's plugged into your computer via USB. We have our graphics adapter. So graphics card, it might be a separate card, might be embedded into the motherboard, and that controls your monitor. But all this stuff is talking to the same central bus. Same central bus here. Okay? Behind all that is our memory. Now, memory is used by all of these different guys to remember stuff in the short run, short term. Okay? So our computer memory is something we use for short-term storage of information as opposed to our hard disks, which is for long-term storage of information. All right, now this part of the picture down here is actually quite important. This is what dictates the speed of our computer. The bus is often our bottleneck. So we can make our processors faster and faster and faster and faster, but if we can only send instructions to it at a certain speed, we're not going to get as much done. Our processors might be sitting there might be this giant line behind it, people waiting to get loaded into the loader for the processor, the CPU manager, which we'll talk about in here. Okay, well, our CPU can't even start working on it until it arrives. So that bus becomes a very important aspect of the whole computer system. So this guy that connects, we need to deal with this on multiple levels. For instance, a CPU requires things to come to it significantly more quickly, or can at least handle things coming to it more quickly than a disk controller, than a USB controller. Graphics cards, they're going to want things coming pretty quick as well. So, how does our computer actually function? Well, we have our input-output devices, keyboards, mice, I guess printers, monitors, all sorts of things like that. And our CPU, these guys can happen at the same time. They can operate concurrently. That's an important thing, right? We don't want our computer to be sitting there and stop doing its work just because we move the mouse. That would be problematic. Okay? Each device controller is in charge of a particular device type. So when we think about USB controllers, USB can actually control up to, a single port can control up to 127 devices. I remember in the early days of USB, people did experiments where they just kept chaining USB devices together. Many USB devices had another USB port on them. If you had a Macintosh keyboard, a lot of the Mac keyboards have an extra USB port on them. But pretty much in the early days, every USB device had an extra port on it. So you could just daisy chain them together. They all worked. That's not that common anymore, is it? When you buy a device that plugs into your computer via USB, it's not that often that it has extra USB ports on it, is it? Why is that? Why do you think that is? How many of you have ever run out of USB ports in your computer? You have more crap to plug in than you have ports. So wouldn't it have been handy if you had some devices that had extra USB ports in them so you can chain stuff together? So why did we get rid of that crap? The who?
Bus
The bus? Okay, what do you mean the bus is too small?
didn't send information fast enough. Couldn't fit as much information.
Nah, I think the bus is big enough. USB is probably has one of the smallest draws on that central bus on our computers. CPU is going to be significantly harder on it. So chances are the bus could keep up. Because when you really think about it, USB devices are pretty simple, right? You think about a mouse. What is a mouse? It just sends X and Y coordinates, correct? And then button clicks. So your simplest mouse has 2 buttons, a scroll wheel. Today, they used to not even have scroll wheels, but 2 buttons and a scroll wheel, and an XY coordinate. So that's 5 integers, 5 floating point numbers that it's sending as often as you click or move the mouse. That's not a lot of data. How big do you think each of those numbers that's sending it? Do you think it's probably an int? At worst, right? Maybe it's a float since it has to do floating point numbers. So let's just say it's 32 bits. 32 bits of data. Times 5. We're not talking about tons of data. So the bus isn't going to get too taken over. Yeah. What else? Why did we get rid of those extra USB ports? What's changed with our USB devices today versus our USB devices in the early days? In fact, actually, USB today is faster. We have even more bandwidth on the bus. Early days, USB 1, anybody know the speed of USB 1? USB 1 was 11 megabits per second, shared across all those devices that transmitted stuff. So you can have 127 devices. Why 127? Where'd that number come from? 127, that should sound familiar to you. It's not just a number picked out of the sky. It actually is related to the software portion of the USB driver. So none of you have ever in computer science stumbled upon the number 127. Nothing?
It's a multiple of something.
It is a multiple of something. I'll give you a hint. Bytes.
The assigned 64-bit integer.
Assigned who?
64-bit integer.
Why 64?
I don't know.
Why you just make that up?
Sound good.
8 bits. The byte primitive type, which is a signed 8-bit number, so that's plus or minus 2 to the 7th power. That's negative 128 to positive 127. All right, so the 127 comes from the index value it's using. It's probably using 7 bits. It's probably using some general purpose byte size register, an 8-bit register on your CPU to keep track of the unique identifier of the USB devices per USB port. All right, so that's why we have that theoretical maximum of 127. Now, USB 1 had a speed of 11 megabits per second shared across all devices on that particular port. So each USB port, assuming it was a hardware port, some of the early USB things, what they did is actually created like 3 ports off a single USB bus. So you were actually then sharing 11 megabits across all 3 of those ports, and then all the devices that were on it, but whatever. It was 11 megabits per second. How fast is 11 megabits per second? How much data can we move with 11 megabits per second? We throw around these buzzwords all the time. USB speeds, USB 1.0, 11 megabits per second shared. We don't measure stuff in megabits per second, do we? What else? Human beings don't typically think in megabits per second, but what else are we sold today in megabits per second? Internet speeds. Why? Why is it given in megabits per second? It's a marketing thing.
Bigger number looks better.
Bigger number looks better. How many of you have a 50 megabit per second internet connection at home? So I have 50 at my house, and it's about to go to 100. So what? Maybe some of you have 30? Who's on Time Warner cable? Let's go that route. Okay.
Super high speed.
You have the super one, you have 50 megabit. Super high or the normal one?
They only let me have like 16.
16. What did you get caught for?
No, it's like supposed to be 20 or 25 or something, but I only get 16 ever.
Well, that's because the places you're downloading from can only feed it at 16. If you do a time test on Time Warner speed test, you'll get your true speed.
That's not true speed though.
Well, no, it's the true network speed they're giving you. So let's say you have a swimming pool, and technically you could fill up that swimming pool at 1 million gallons a second. But the hose only feeds stuff at 1/10 of a gallon per second. You know what I'm saying? So what they're selling you is bandwidth, but you can only receive stuff as fast as whoever you're downloading from can deliver it to you.
Yeah.
So your download speed is somebody else's upload. So if you use Time Warner speed test, you'll be working directly on their network and find out what your allocation is in terms of capacity, what your theoretical max is. Then everything else is a... He can.
If you download through Steam, then that's what you should...
Assuming Steam can give it to you at that rate.
Can.
Okay, well, so if you're not getting that, then there's something else going on.
Oh,
Yeah. Okay, but it's probably not uncommon for you to have 30 megabits per second at your house, right? So those of you, how many of you in here knew what your internet connection speed is? Off the top of your head, actually knew it. Right? Everybody in here should. Okay? As technologists, we should know the kind of technology we're using. Otherwise, we're just like the other,
Idiots.
no, they're not all of them are idiots. Some of them are idiots. But we're like the steerage of humanity. I think that's actually worse than just calling them idiots. I think that's actually a fairly elitist view. So computer scientists are one thing, and then everybody else is steerage. All right, so in any case, we should know about the technology we're using. Now, when you've told people, those of you who raised your hands, and somebody asks how fast your internet connection is, how many of you have ever said, oh, it's 30 megabytes a second? Interchanging megabytes and megabits. Did you know there's a difference? If you got 30 megabytes per second, that'd be pretty sweet. I don't even get 30 megabytes a second. My maximum download speed is something like 6.7 megabytes per second. Is my theoretical max. So 11 megabits per second, that number, is actually equal to, if we want to put this in kilobytes or megabytes, 11 times 1024, that gets us kilobits, times 1024, that gets us bits, right? Divided by 8 gets us bytes. Divided by 1024 gets us kilobytes. So that's 1,408 kilobytes a second. Divided by 1024, 1.375 megabytes per second. Seems less impressive, right? So 1.375 megabytes per second shared amongst a maximum of 127 devices.
Is megabytes per second shorthand a capital B?
Yep, capital B. So if we're just going to go back here and I put in my 50, there's my 6.25 megabytes per second maximum download speed. Those who have 30, 3.75 maximum download speed. How many of you are on AT&T? One of their DSL providers. Do you know what your speed is? 20? Be surprised if it's that high. It is possible. Uverse had just put in some new circuits that actually can do that high, but you basically need to live at the AT&T store. Not the store, but their central office. And it's not a negative on AT&T. AT&T uses the DSL-based technology instead of cable modem. Different type of technology. And it's much more based on distance from the home office. So it's not that AT&T's stuff sucks. It's their technology is different. And if you live at the AT&T home office, well, then they can just hook an Ethernet cord up to your house and you're kind of good. But the less distance it has to travel over copper wire, the best. Because DSL, the technology you're using for Uverse, is actually, I don't know, maybe the grandchild of dial-up modems, dial-up technology. So when we had a modem that talked over, a telephone line, our fastest speeds were what, 56 kilobits per second, little b, 56 kilobits per second. And that was roughly 4.5 kilobytes a second, something like that. So when that was our fastest speed over that, our DSL today is coming over the exact same telephone line. What's the difference? What's the difference between our dial-up technology before that was 56 kilobits per second to our, here just to give you the math on that, 56 kilobits times 1024 is bits, divided by 8 is bytes, divided by 1024. Oh, times 8, thank you. Times 8, that's our, no. Bits divided by 8, that gives us bytes, times 1024. Divided by 1024, so you confused me. Divided by 1024 gets us our kilobytes per second, right? So that's 7 kilobytes per second, theoretical maximum speed on a 56K modem. Or a lot smaller than that, megabytes per second. So that was over telephone line. And let's just say that The fastest DSL today, let's be fair and say maybe 18 megabit per second. That's going to be a pretty solid DSL connection, but let's just call it that. Okay, so that's 2.25. Hold on, I need to do one more multiplied by 1024 because that was in megabits, right? So that's 2,304 kilobytes per second. And if you want to divide it by 1024 again, there's your 2.25 megabytes per second. The exact same medium, telephone line. We went from 7 kilobytes a second maximum speed to 2.25 megabytes per second speed. What changed? It's actually related to the architecture course right now, 325.
Cages?
Huh?
Fiber optic cables?
No, it's the exact same cable. So the exact same phone lines that I used to do dial-up on can now be used for DSL and transfer stuff at 2.25 megabytes per second instead of 7 kilobytes per second max. What's changed? This gets back to something Dr. Locklear says. It talks about the grand ideas of computer science. All these classes are related. We're just looking at the field from a couple different angles, right? From 8, 9, 10 different sides.
So digital versus analog.
Digital versus analog. So dial-up modems. A modem is a modulator-demodulator. It converts between analog and digital and analog. So the actual signal that was being sent over that phone line in dial-up days was an analog signal with lots and lots and lots of noise. Okay? Digital, DSL, digital subscriber line, sends a digital signal over that same piece of copper. It's the same wire we're transferring stuff. It's how we're transferring over that changes. Okay? But DSL is very susceptible to signal loss over distances because copper, the signal does weaken over copper. Even though copper is a conductor, it only conducts so well. You can't run 1,000 miles of copper, hook an electrical current up to one end, and expect to electrocute somebody on the other end.
This isn't.
I mean, that's a good example, is what I'm getting at. Okay, and that's putting a lot of power at the one end. In this case, we're just talking about sending some internet stuff, okay? So they actually have something called a piece of equipment called a Dslam, which they put, they have the home office, which is the source of the internet. Then they put a Dslam at a certain distance, which is a repeater. So it reads in the signal and then rebroadcasts it. That way they can extend it out and give you higher speeds farther away from the home office. A cable modem doesn't really have that problem where the signal degrades to an extent. I mean, we run a cable modem 1,000 miles from the home office, you're going to have some degradation of signal, but it's not nearly as susceptible to it. So 11 megabits is 1.375 megabytes per second transfer rate. Okay? So, and that's shared across all of the USB devices on that chain. USB 2.0. What was the speed of that guy? Twice as fast? Huh?
500 megabits a second.
500 megabits? It's actually not far off. A little bit low. (800 megabits per second, also shared. So now we're at 100 megabytes per second shared. Big boost in speed, right? What about USB 3.0? This is the newest, latest, greatest. It's in gigabits per second. Say 3. I think it's 6 gigabits per second, also shared. One thing I would say about anything USB, USB is what's called a parallel technology.
It's 5.
It's 5. Parallel technology, which means it's bursty. Bursty. So you might have maximum speed 1 second, and then almost nothing the next. Because it's sending stuff, parallel sends stuff 8 bits at a time. 8-bit bursts. Where serial technology, any of you heard of Firewire? Called a competitor to USB. Kind of fallen off now, right? Everything's gone to the newer USB. Firewire was a serial technology, sends 1 bit after another, serially. So Firewire 1 was actually faster than USB 1. Firewire, the original, was actually about 400 megabits per second. But then they came out with USB 2, which was twice as fast as Firewire. But you probably still had graphic designers, video editing people, who still used external Firewire drives as opposed to external USB 2 drives, even though the USB 2 drives had a faster speed. Why is that? Why would you use a device that has a transfer speed of maximum speed of 400 megabits per second over a device that has 800 megabits per second? Twice the speed. How would you choose to do that?
Because you're an Apple fanboy and don't know better.
No, nothing to do with that. Specifically in the video editing industry was really where this existed. Dealt with encoding video. USB being a parallel technology and being bursty, you would lose quality in your video as you were encoding it, because video encoding happens in real time. Okay, that's why we need the big beefy Mac Pro machines or the Dell servers that have 12, 16 processors in them, that kind of stuff, so it can do all that work in real time and keep up. Well, if you had a bursty stream of data coming in, it was hard for it to maintain a consistent bit rate on your video. So you actually might have hiccups in your video. Well, with Firewire, you get a very consistent speed because it's 1 bit after another. Does that make sense? So even though it was a slower transfer speed, it had a much evener, much more evener. Evener is not a word. No, not a word, definitely not. Okay, a much more even, most bestest stream of data coming in. And hopefully get a more consistent encoding on the back end. Okay, so USB 3. So that's 5 times 1024. So that's 640 megabytes per second. Keeps getting faster, 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 faster. All right. Now, back to the original question. Why is it that our early day USB devices that were only based on 11 megabits per second, far less speed, often had a secondary USB port so you can chain a bunch of them together? And the current ones that are based on, super commonplace today, USB 2, right? Any device you get today is going to be USB 2. More and more now are USB 3. But even the USB 2 devices, which were, 70 times faster? I'm just roughly doing the math in my head, it's probably close. Which were 70 times faster, they didn't typically have the extra USB port to chain a bunch of them together. Why? Is it a funny thing, or is it related to class?
You're really close. It's 72 times faster.
72, well, I am a genius. Remember, that's why I'm up here with the tie. So you're impressed I was close? It's a reasonable guess, wasn't it? I actually knew the exact number. I just fudged it that way you guys wouldn't be too impressed. Like, okay, well, that's not human. So why is it? Why have we dumped the extra port? There's a side of USB we're skipping here, which we're going to more generically talk about, a side of peripherals associated with computers. How many of you have a USB mouse? Okay. Plug in the USB mouse and you look at the bottom of the mouse, look directly at it. Right?
Light.
What do you see?
Red light.
A light. What does it take to make light? Power. Takes electricity, right? USB supports a current. So we have USB powered devices. How many of you have ever gotten a USB device that also had an external power supply? You had to plug it in over and above the power that the USB port was given, right? Why is that? Because it was drawing more power than the USB port could do. More and more USB devices are relying on some level of power from that USB port. How many of you have a jump drive? The USB stick drives, right? A lot of them have lights on them, right? You plug it in and it lights up, meaning, ha, I have electricity. Go, turn it on, right? And then if you get the little mobile, bigger than the USB stick, but like a Western Digital, I think they're called passports, right? They're kind of the smaller laptop size hard drive, but still portable. And that guy operates just off USB, correct? But when you get the bigger, what are the big ones called? They're not called passports, are they? They have a different name, something similar. Well, whatever, you know what I'm talking about. Bigger external USB drives that have a desktop hard drive in them, they have a plug-in. They don't just power off the USB, do they? You actually have to plug them into the wall. They require more electricity to run. Because the USB port itself, that single port, wouldn't be able to power that device, let alone daisy chaining some other devices off of that. Now, realistically speaking, could we take a jump drive and probably also power a mouse off that? I don't know if the answer is officially yes, but probably. Sounds like that would probably be possible. Mice don't seem like they take up very much power. USB drive can't take up very much power. That's kind of the trade-off. That's why they're based on flash memory and have a much smaller capacity. But one of the reasons why we've done away with the daisy chaining of USB devices is we're not just dealing with the problem of bandwidth. We're also dealing with the problem of shared power. Okay? So kind of an interesting thing to consider with USB. Each device controller is in charge of a particular device type. What's a controller? We hear the word device or the phrase device controller. What does that mean? Controller is used a lot in computer science speak, whether it's programming or hardware, whatever. We have this phrase, we have this word controller. What does it mean? How many of you have ever driven an RC car? Or RC boat, or RC anything? You have a controller. What does a controller do? Controls it, right? It drives it. Tells it what to do. You turn left, it turns left. Push the little stick. Although new ones, right? The new ones have the steering wheel thing on the side, right? It's like the trigger, and then you have the wheel to actually drive it. You know what I'm talking about? Oh. When I was a kid, RC cars, you flew them like a kite. So when I was a kid, you had the one that had the left-right stick and then the forward-back stick. Do they still make those? Yeah. Oh, 'cause the only ones I've seen, I don't know, 4 or 5 years ago, I was into gas-powered RC stuff. My wife made me get rid of it after I exploded an engine in my garage. There's actually a video on YouTube of that happening.
Is that on your call?
It is. It's on my channel. You can go look it up. It's me messing with it. And all of a sudden the engine just goes crazy, and she says, "Do you know what you're doing?" Because it doesn't look like it. You just see this engine just screaming. It just sounds like it's about to explode. But in any case, it had like the trigger like looked like a gun, but had a wheel on the side of it for controlling it. And I wasn't as good at controlling it with that. But in any case, what was I talking about? Oh, controllers. So, what's a controller as it relates to computer hardware? What's a USB controller? We just talked about in this previous slide, or one of these slides, we talked about the USB technology. This is the USB bus, if you will. But what's a USB controller?
Does it control all of the USB devices?
Something has to sit between that bus, that all communication, where all communication occurs on your computer, on the motherboard, that bus, and the actual USB cable, which is plugged into a USB device. Something has to speak the USB language. That's what the controller is. The controller translates between USB language and, hey, I know how to work with the motherboard's bus language. Make sense? So, that's what a controller is. Where have you heard controller in any of your software classes? How many of you took the iPhone programming class? Okay, where do we hear controller in there?
Navigation controller.
Navigation controller, view controller. Okay, what's a view controller? Controls a view. It's crap associated with a view. Things, so did you find the video? So you put your volume up and play it.
No, I don't have enough.
Oh, you don't have it up? Okay. Okay.
Do you know what you're doing?
Well, you missed the last part.
That was it.
You laughed through it after she said, "Do you know what you're doing?" And she goes, "Well, because it doesn't look like it."
Just look at reaction. Like, starts really going. You're just like back away.
You don't look like it. So that's why I'm not allowed to have gas powered things anymore that I get to mess with. What's up?
Electric power.
What fun's that? They don't go as fast.
Okay.
I don't think so.
Unless you're driving a Tesla.
I think that's even still true. I don't think you have like any electric power, like drag racing cars or anything. I think, aren't they burning like pure alcohol or something? Like they just throw gas mileage out the window. We get 0.1 miles per ton. We just need to make it from here down to the end of this road. And we don't want to have any fuel when we're left because we're probably going to explode. And they have the giant tires in the back and the little tiny skateboard tires in the front. Love that. Get one of those and drive it around town. What was I talking about? Oh, USB. So controllers. They control devices that can act as a translator between something and something else. In our case, it translates between, for the USB example, USB language, which is, think of it like XML or something, but USB predates that. But some sort of data representation language that says, here's a USB device, here are the 12 things that USB devices can say. Okay, 12 different variables we can set, and each USB device maybe deals with it in a different way. I'm just using 12 as an example. I don't know exactly how many variables USB devices can talk, but think we have a mouse, and an individual mouse can choose to set up to 12 variables. Okay, let's use that as an example. That controller is going to read in those 12 variables, or the subset of them. Maybe the mouse only uses 4 of the 12. Now the driver, which is a piece of software, it's going to talk to the controller and it's going to interpret what those 12 variables, or the subset of those 12 variables, what it actually means for that device. So you have these programmable mice that have, a zillion buttons on them, and you can control what each button is, and you're actually configuring the driver. You're saying this little side trigger button, when I click that, this is one of the 30 things it does. I'm going to make it do this thing. Okay? So that's the software, which talks to the controller, which talks to the device, and that's a two-way communication. So when you push that button, the device lets the controller know these variables just got set. The driver then says, oh, this is the variable that was set. This is what I should do. It lets the bus know when your magical thing on the screen explodes or fires its missile or whatever it is. Get how all that works together? Lots of moving pieces inside that sandwich that is the, I guess, your computer. Each device controller has a local buffer. What's a buffer? Another buzzword. These are all like vocabulary words we might run into. What's a buffer?
Prep the data.
Who?
Is it prep the data that's transmitted?
Prep the data. Okay. It
Stores it.
stores it. Buffer is a little tiny memory storage. Okay. Usually when something's called a buffer instead of memory, it probably isn't real big. Okay. Little tiny chunk of memory to keep the costs down more than likely. But it stores memory temporarily. And why might we want to buffer things? We buffer stuff all the time. How many of you watched Netflix in the last week? Netflix buffers stuff, right? Why? So your crappy internet connection can keep up. You hit play, what does it do? It sits there and thinks for a while it's buffering the show. So it loads the first 5 minutes of the show, let's say, before it actually starts playing the show. That way you have a 5-minute buffer, so your internet connection just needs to keep up within 5 minutes so that from your perspective, it's a seamless show. Does that make sense? Same thing's true here. But buffers make sense for some devices, but not all devices. When you use the mouse, are you okay with a 5-minute delay? No biggie, right?
It's on Mars, it's okay.
I mean, it's one thing to say that we can't have a delay with games, right? But even Microsoft Word. Would you deal with a 5-second delay in Microsoft Word? You would just quit, right? So any sort of delay becomes problematic. So buffers make sense for some devices, but not all devices. Printers. Does the buffer make sense for printers? Yeah, you're printing a large file. Let's go ahead and buffer it into the memory space so that when the printer starts pulling from that buffer, which should be very fast, it has constant data it can pull and start printing line by line, that kind of thing. So in that case, if you send something to the printer, it usually doesn't start printing instantaneously. There's usually some sort of delay, whether it's 5 seconds or 10 seconds. A big print job may take 30 seconds, whatever. But we're okay with a delay like that, right? As opposed to our printer printing half the page and losing the rest of the data. And it's like, this is good enough. All right, questions about any of that? I was going to give you an assignment today, but I think I'm going to give it to you on Monday. All right, I will see all of you on Monday. Don't forget to tip your waitress.
Over.